Sure. Hi everyone, I'm Niv Haim, and today the subject of the talk would be Introduction to Adversarial Examples. I assume that some of you have heard of it before, but I also assume that none of you have heard anything about it. So this will be an introductory to the whole subject. And let's start with the most popular experiment that people normally think of when they hear the word adversarial example. And I'll tell you what I did. I downloaded this image of little piggy from the internet, and I fed it into one of the off-the-shelf classifier, Resident 50, I think it was. And it told me there is 98% chance that there is a pig in this image. This is not surprising because we all know that modern neural classifiers are very good at classifying images. Then I added this random noise, simulating noise to the image, which is much smaller than what you see here. This is magnification by 50 of the real image. And then I got this image, which all of you probably think is a pig. But when I fed it into the classifier, it told me there's in fact 99% chance that this is an airliner. And if you've asked, what are the chances that the classifier thinks that this is a pig? So this is how confident the classifier was that there is a pig in this image. Now, this is definitely not a random noise there. It's very carefully tailored to this specific image in order to fool the classifier to make it think that there is actually an airliner in the image. And this experiment was shown by a few people, by these fellows, a few years ago, by Biggie, Osagedi, and Goodfellow. And yeah, this is probably what most people, when you tell them that this talk is going to be about adversarial examples, that's what they would think there will be in the talk. So let's see what we're going to talk about today. We will see adversarial examples. So we've already seen one. That's an adversarial example for classifiers. We will discuss what they are. We will learn how to generate adversarial examples. And we will learn how to defend against them, or actually maybe defend against them, and we will talk about it further. And we'll see some cool properties and advantages of adversarial examples. So let's do a brief recap of training neural networks. And the first thing you do is you take a bunch of images and you're going to feed it to your classifier. And let's call it f with parameter theta. And we want to tweak the parameter theta of the classifier in order to make it to classify better, right? So how do we do that? We use the loss function, which gets the outputs of the classifier and the true labels. And the purpose of this loss function is to tell us how well we classify images. And for example, the most common classifier for classification is the cross entropy, which I'm sure all of you have seen, which is a function of the outputs of the classifier and the true labels. So we want the classifier to classify better. So we want the loss to be smaller. I'm going to minimize the loss, right? How do we normally do this? We do it by gradient descent, by following the negative direction of the gradient with respect to the parameters theta. Yeah, so this is all of you, I guess, have seen and you know, perfect. Now, when we want to generate adversarial examples, we disregard the parameters at all. So we're going to take some off the shelf or some pre-trained classifier. Someone classified it for us. And we are not going to touch the parameter theta. So from now on, it's going to be only f, function of the input. And let's see another example of another pig I downloaded. I hope you like pigs. And for this pig, Resident 50 told me that there is 90% chance that there is a pig in the image. And we want to fool this classifier. We want to make it think that there's something else. And remember, a bad classifier, we can use the loss to see how bad the classifier is. So we can somehow take this loss, add this noisy image that you've seen before, and we want to tweak this delta, this addition, in order to maximize the loss, right? We want to make the classifier classify worse. And how are you going to do that? So we are going to follow, again, the gradient of the loss, but note that this time, we take the gradient with respect to the inputs, not the parameters. We don't have any parameters anymore. So we're only going to change the input, actually only going to change the delta in order to make the classifier act worse on this image. And right? We want to maximize the loss, so we're going to follow the positive direction of the gradient with respect to the input. So yes, this will tell us how to maximize the loss. So right, we want to take the delta and follow the gradient at each step. And let's see what it does. Let's see what it will happen to our image. So here is our image, and here what happened when I added the gradient to the image. And now I see.
How do you know the label?
The label was 90% pig.
Ah, so you'll take it from the classifier.
Yes. The loss with the true label. So now instead of having the 90% pig, we have now 70% hay in the image, which kind of makes sense because right there is hay in the image, but it's not a pig anymore. It's not the correct class. And when I went a bit further, so now I added 10 times the magnitude of the gradient. Now I get this image, which is, you can see some noise on it. And you see that the confidence of the classifier is now worse. So instead of being very confident that there is a pig in the image, it now says 45% there is a pig. And if we will continue this direction, so adding 100 times the gradient to the image, and now we managed to get the classifier to say that there is 45% fire guard in the image. But you can see what happened to the image when this happened. By the way, if you follow the gradient 1,000 times, you get this incredible image, which is apparently 100% spotlight. So, did we generate an adversarial example? Is any of these photos an adversarial example compared to the other adversarial example that you've seen, right? We managed to take a pig and make it an airliner. What do you think?
In the second
no, I see no's. Yes. Okay. So actually, I want to make like a small discussion on what is an adversarial example. So we will need some definition for this. Let's try a possible definition, which is any input that fools a computer but not a human. But that might be a good definition for the adversarial example. So let's see a few examples for this. So we already seen what happens when you take a real image and edit some noise, and you definitely manage to fool the computer but not a human. But what about this noisy image of the pig? So it still goes into this definition of, I think all of you would know that there is a pig in the image, but the classifier thinks that this is a fire guard. What about just random noise image? All of you would tell this is a noise, but the computer thinks that this is 26% spotlight. What about just model failures? What about just images that the classifier fails to classify? And just random images that were not supposed to be fed into the classifier to begin with, like out of distribution images. So my point is that this definition needs to focus a bit more. And I want to say a word about the bigger picture here, which is failure modes in machine learning. And there is this nice blog by Microsoft guys, security Microsoft guys, and they did a very long list of failure modes in machine learning. And they divided it to mainly two ones, intentionally motivated failures and unintended failures. Where intentionally motivated failure, there are a whole bunch of different attacks that you can do to your classifier, to your machine learning model. And there's also a lot of unintended failures, like you just get the wrong classification, right? And we are going to focus only on this failure, which is perturbation attack, which is probably what most people think of when they hear the words adversarial example. So it's important to remember the bigger picture, and that we are going to focus on these perturbation attacks, which is when you take a real image and you add a small delta to the image in order to fool the classifier. Now we are going to also focus on image classifiers. Remember, there are a lot of adversarial attacks or examples out there for non-classifiers, like image segmentation, detection. Basically, every machine learning model that goes out there, some people will try to fool it. So this is going to be our focus for today. It's going to be perturbation attacks for image classifier. So we saw adversarial examples, we discussed what they are, and now let's learn how to generate these adversarial examples. So what we actually want, right? We said we want a small noise, which is not what we got here with this example of the pig. And what is small delta? How can you define a small delta? So one way to do it is to bound the delta by its norm. And it could be any norm, but the most typical norm people normally use. Again, there are a lot of papers out there of a lot of norms, so but I'm going to charge only the most popular things here. This is the infinity norm. And how does a vector which is bounded by infinity norm of epsilon looks like? So the vector could have any value. For example, epsilon is 0.1, could have any value between 0.1 and minus 0.1. So any values between these can go into this vector, and it will be considered bounded by infinity norm of 0.1.
Niv,
Like,
delta isn't
yes.
a matrix?
Sorry?
Delta isn't a matrix?
It's a matrix, but I don't use any matrix property of it. It's basically just, I can call it a vector or matrix, tensor, whatever you like. It's just a bunch of values in the end. And when you bound it as a vector. It's not the norms are not specifically interesting for something like matrix. You don't know like spectral norms or stuff like that. It's just bounding the like it's a vector. You just add it to another image. So how are we going to combine our requirements for small delta? And that delta will be some function of the gradient, which we've seen is going to make the classifier act worse, right? How are we going to combine this? We want to enforce this gradient to be small. So let's start with the gradient here. And this is an example of how a gradient can be. It can have all sorts of values. There is no guarantee that it will be bounded in any way. And the next thing, we are going to take the sign of the vector. So you see each value here, it's pointwise. Each value would become its own sign. So if it's positive, it's going to be 1. If it's negative, it's going to be -1 and 0 otherwise. And now we're going to multiply this by epsilon. And what we got here is a vector delta, which is bounded by infinity norm of epsilon. Great success.
Niv,
yes.
I have a question. Like, in the beginning, you said that we will take the gradients with respect to the delta, but all the time you write
input. Yes.
Yeah, with respect to the input, and then you said that actually to the delta. But now you write the gradient.
I see. Okay, that's a good question, and I thought you were going to add another thing here. So yes, so you take the gradient with respect to the input, but the input is x plus delta. And the gradient flows to this x plus delta. X is going to be fixed, and you're just going to change delta. So it's the same gradient go to the delta. You can think of it otherwise, that you only have the input and you change the input, or you can think of it that the input is x plus some delta that you're going to change, and it's all equivalent. You're going to get the same gradient for all of them, right?
So you're taking the gradients with respect to the whole input, but changing only the delta. So
yes.
Okay.
Yes.
Okay. Mm-hmm.
Yes, it's equivalent basically. Okay, so this method of taking this delta to be like that, which is small and a function of the gradient, is called fast gradient sign method, also known as FGSM, and was proposed by Goodfellow a few years ago. And before I go further, just a very small note, which I'm not going to delve much deeper, but you can think of delta, you can derive it otherwise as what maximizes the local approximation of the loss function. So I'm going to leave it here on the slides, and if you want, you can take it. It's really cool exercise to do by yourself, by the way. So that's it for the moment. So there are two ways of thinking of it, but you can take whatever you like. Let's see some examples of it, numbers and images, how FGSM looks like. So I'm going to do an example here on MNIST dataset, and I train this classifier. By the way, almost all the stuff I show you, it's stuff that I did on my own. I really trained stuff, and I did it other than stuff that I cite people. So this is like true stuff. So I trained this classifier, and I can send you the code if you want it later. This small classifier, which is the 2 convolutional layers, 2 linear layers on the MNIST dataset, just to make it a good classifier, right? Like you normally train stuff to be a good classifier. And this is what I got. This is some samples from the test set and the predictions. And you see that in most cases, other than this little one here, most cases the classifier acts very well. It managed to classify the images correctly, and it's very good. Now let's generate an adversarial example using the FGSM. So we want to generate an adversarial example X by taking a real image from the test set, or some other, it doesn't matter, like a real image of a digit, and adding it a small delta. And this is how the delta looks like when you do the FGSM on my classifier that I trained. So when I added, I got this image. And this is an adversarial example for this classifier. So now let's see how it looks for all the images. And you see that now when I feed these images to the classifier, while most of you, I'm pretty sure, would know the correct digit, the classifier gets most of them wrong, or like 50% wrong. So totally, the numbers are, the test error, the clean test error is 98%, but the FGSM error, so this is taking the test set and instead of feeding it, you take the adversarial example generated by FGSM, then you feed it to the classifier. What do you guess the error would be?
50, no?
50? Oh, that's a good guess, right? Because you see this here, but it's actually 40. For this example, it's 40%. And it's important to say also the epsilon, which is 0.1 in this example. All the images, the pixels are between 0 and 1. So I took epsilon 0.1 here. And you see that FGSM, even though it's very simple to compute. It's very simple, fast, and vicious. So even on this very simple example, it got our classifier to be wrong on 60% of the test samples. And if you want to the code or some other interesting stuff, I took it from this site by Zico Coulter from CMU. What can we do to defend against FGSM? Any ideas? Any ideas?
Can I have a question before?
Yes.
So you must have the model in order to build like a
That's correct.
Right?
Yes.
Adversarial. So it's not
Yes.
so easy to cheat a network because you must have its.
That's a good question, and we will touch it hopefully down the road. But at the moment, I'm generating an adversarial example using the model. That's correct. I need the gradient, and I need the model, and I'm going to generate them using the model. But okay, so any ideas what we can do to make the model more robust to this?
You can train the model with adversarial examples.
Yes, that's very correct. So we can use these examples and feed them into the classifier. This is called adversarial training. And what do I mean by that? So I'm gonna take all these adversarial samples and gonna take, for example, these 4 while training, and tell my classifier I want this to be 4, not 7. I want to classify these images well, also with the images, the other images. So I'm gonna take this. I want it to be 3. I want it to be 7, and so on and so on. And we're gonna train on the adversarial example, which is kind of augmentation. I want to stress this part because some people miss this. So what happens in every batch, I'm gonna get some images. I'm going to generate adversarial examples using these images. And I'm then gonna feed these adversarial examples into the network and make a step and get the next parameters of the network. Now I'm going to get the next batch. I'm going to generate again the adversarial examples and feed them into the network. And I want you to see that at each step, I'm using the current status of the network. So it's not that I'm generating adversarial examples at the beginning of my training and then using them. It's at each training step, I'm generating new adversarial examples, then using them to train my classifier.
And you do this from the beginning of the training, right? So
that's correct. Yes, that's correct. Yes.
In this example, I don't understand why do you call it adversarial examples, because it looks like completely you lost the perceptual similarity to the dataset, right? So it's
adversarial example because you will recognize that there is a 2 in this image, but the classifier most probably would think there is something else. Like before. That's why it's so.
The example of the pig, because it's very easy to distinguish between perceptually it's very different from the training data. So it's more like.
Yeah, but the classifier has no idea what you mean by perceptually. It's true that you can think of other ways to define this model specifically for MNIST, but I'm showing the MNIST example. But the classifier doesn't know how an MNIST digit looks like, or you can feed it with anything, right? So this image is supposed to be 5. It's very close to 5, but with the bound infinity norm bound. But the classifier would probably think it's not 5 here.
But in this example, it looks like more like we would just feed the network with different digits that are not MNIST.
But it's not very different. It's very, very close to the real image. The difference here between the real image and what you see here is only 0.1 out of 1 for each value. So each value can be between 0 and 1. And I only change it. I added noise which is at most 0.1. It's very small noise.
It's close maybe in the, I don't know, L2 norm or something, but it doesn't, it's not in a.
But so you define closeness in different metrics, but which is probably kind of perceptual because you know how it should look, but the classifier does not know. So you have to somehow define what closeness mean, and that's what we use. But also it's a disadvantage because of course you can use other closeness metrics to attack it, and then I mean we are now focusing on this specific definition. Okay, so let me go on, please. So let's see the numbers. Using the standard training, the test accuracy was, if you remember, was 98%. The FGSM accuracy was 40%. But when I did the adversarial training, then the test accuracy is still very well. It's 97%. And you see how the FGSM accuracy now has improved drastically. So now it's 94% instead of 40 that was before. Right? And this is just training my classifier. We're using adversarial examples. So,
but are these adversarial examples from the first iteration?
Yes,
or
from the first iteration, all the time.
So, but if someone would want to attack the networks, then they
could use other methods to attack. So, okay, that's my question. Did we solve the problem? And you kind of answer it. So people can use all sorts of attacks, right? We don't necessarily have to use the FGSM in order to attack our method. We can attack it otherwise. So let's see about that. And we learn how to attack with FGSM. We learn how to kind of defend with adversarial training. And let's get a better picture of how it looks. And for this sake, I'm going to assume, just for simplicity and for the sake of being able to visualize things, let's assume that images are 2D objects. They're not, they're very high dimensional objects, but let's assume our objects are 2D by classifying 2D objects. So every image is lying on the 2D space. And we are adding these small deltas to some example. So how does it look when the delta is small in infinity norm? It looks like this, right? So when my delta is bounded by infinity norm of epsilon, in each dimension, the delta can move at most epsilon. So it looks like we are trying to defend each image in this small box, small epsilon box around it. And let's see how FGSM looks like pictorially. So we start from this image of 4. This is the formula of FGSM, and we are making this small step. We're going to get there, and we're going to generate adversarial example. And we found something which is possibly an adversarial attack, but there may be a lot of other adversarial examples out there which are still allowed. So these are small perturbations in this box. We only need to find them. So this is the problem. So the defender has to defend in the box, and the attacker needs to find adversarial examples in this box. So in a moment, we're going to talk about a better attack method, which is called PGD. But before that, just a brief note about optimization and how it looks from the optimization view. So this is kind of the game of adversarial training. This is what we did when we trained it adversarially. At each step, we wanted to defend against possible attacks. And this could be formalized as a minimax optimization problem, which is this. In a moment, I'll talk about it. But I want to say that this was proposed by Madri a few years ago with this paper, which is a great paper. And really, if you only have one paper to read in adversarial examples, let it be this one. It's a really great paper. So you can formalize adversarial training with this optimization problem. So let's just skip some parts of it. And what we get here is just standard loss. This is the loss right here. And you're going to minimize the loss. You're going to tweak the parameters of the classifier and minimize the loss over the whole data set. And what we are doing when we are training adversarially, at each step, we are just adding some delta that are taken from some sets, all bounded deltas. And we want to find the delta which would maximize the loss locally. So that's optimization. That's the optimization view of adversarial training. So you can look at it as kind of adversarial loss. And now a small note about my illustration. I showed you here that there might be a lot of adversarial examples in the box. But to be more precise, this is how things looks like in reality. So there would be regions of adversarial examples. So let's say if this is a correctly classified image, there will be a region of correctly classified images near it, but there might be regions inside our bounds which would be wrongly classified. And note about my note on illustration, this is only an illustration. So I just drew this line before, and who knows if this is how things looks like. When you see experimental illustration, some people think it's enough to show you just the illustration. It could be quite misleading. So always ask yourself if you can make it not illustrative, the experimental result. Or I like to cite the motto of the Royal Society here, which is nullius in verba, it's trust no one's word. So better if you can just try it yourself. Luckily, so enough with the scientific propaganda. Luckily for us, we have this illustration here. This is a true binary classifier on 2D objects. And you can see that how this looks like in truly 2D images, 2D objects. So you see all adversarial examples lurking out there, waiting for someone to find them near the true objects. And this is how it looks like after doing some adversarial training. You see how now there are no adversarial examples near each object. And again, some 2D alert. This is very good illustration. It makes some idea about this, but in real life, things get much more complicated because images are high-dimensional objects. Okay, so let's talk about PGD, how it looks like. So we've seen, or PGD, or which stands for projected gradient descent, or also known as Iterated-GSM, which you will understand in a second. And FGSM, we saw that it just makes one step towards the boundary, while PGD is going to do some optimization problem and to find maybe a better adversarial examples in our allowed region. So it kind of just solves this maximization problem locally using gradient descent. So how it looks like, the attack model is now allowed deltas are all deltas which are bounded by infinity norm of epsilon. The FGSM makes one step, right? We've seen this already. And the PGD would start from the image and would make these steps. So what you see here is again the same equation, the same formula for FGSM. The only difference here is that I take an alpha instead of epsilon. There, you see the gradient, you take the sign and you multiply it by alpha, which is normally a bit smaller than epsilon, but this is a parameter you can tweak. And you're adding it to your current guess of the adversarial example. And this is how you train it. Yes, so let's see how it works. It starts from first step, you get some adversarial example, which is FGSM, and then you continue doing the next step. The important thing is to just clip your optimization problem so it would not leave the allowed region. And then you continue again until you get your desired adversarial example. So this is PGD. And let's take a look how it looks with numbers. So we've seen this table already of standard training and how we improved our robustness using adversarial training with FGSM. And now when I attack my model with PGD, you see how the standard training reduced to be very low. And also we managed to reduce the accuracy of our adversarially trained FGSM model. So what can we do to defend now?
May I ask a question about this number? So this is all on this very simple NIST data set. Does this number compare to like the real world data set?
Wait for the next slide. That's a great question. So any ideas, but what can we do to defend now?
Again, train with adversarial examples.
Yes, exactly. You can train adversarially using the PGD, and that's what you're gonna get. So the test accuracy is still quite high, FGSM is still quite high, and we also improved the PGD accuracy. And that's a good question by Raphael, how things looks like in reality and not only on the MNIST dataset. So let's look on some other datasets on the CFAR 10, I did exactly the same experiment. Not me, I took it from some, again, from Madhuri's lab citations. And you see on CFAR 10, the standard training test accuracy gets you 95%, which is kind of good. PGD with a small epsilon, so each pixel here is now between 0 and 255. So epsilon of very short, very small part of it would put you in basically 0%. So PGD would just destroy your accuracy of your network. And training using PGD, adversarially training, you get the test accuracy is reduced, but the robustness accuracy is quite good, but you see it's not as well as the test accuracy. And if you do the same on ImageNet, then these are the numbers. The standard training again is 76%, while the PGD kind of destroys your accuracy. And doing adversarial training, you see that you get 90%, which this is why I said that we are going to learn maybe how to defend against adversarial examples, because you see, we didn't really manage to make our classifier robust. And this is an open question in research. So how do you make your model robust? Yes.
So Niv, it's not only not robust, it's also pretty bad on the original test set.
You are correct. Yes. So actually, we kind of destroyed the original test accuracy, and this is also an open question whether there is a trade-off between making your model robust and still staying with your current accuracy. And there is some good papers. There is one example where you showed it specifically that there is such a trade-off, but generally, I don't know if there is a good answer to that. So we've seen how to attack with FGSM and PGD. We've talked a bit about the optimization view of adversarial training, and all these, well, I'm going to come back to Yochai. I think Yochai question it was. All these were white box attacks where I knew exactly, I had the model, I could compute the gradient, and I could do whatever I want. So we're gonna talk briefly about black box attacks. And as I said, white box is where you have the model, you can compute the gradient, you can do whatever you want, like FGSM and PGD, etc. And black model is where you don't have the model, you can only feed it inputs, but you cannot have the gradient. So think of some online image classifier, or there is like this deep nostalgia by MyHeritage that you can upload the images and it would do all sorts of cool stuff to your faces. But if you upload an image of the dog, so it will tell you, okay, there's no face in the image, but you cannot get the gradient in order to make the dog looks like a face. It's a black box. So what can we do? So we cannot get these attacks that we've seen. What can we do to attack black box models? Let's put our black box here for a moment. So we can take another model of ourselves, train it on what we think is the same data that the black box model was used to, generate adversarial example using this model of ours, and then use it to feed it to the black box. So this is one method that you could come up with if you are trying to attack black box model, right? The question is, will it work? Will it make the black box model break? And then again, some numbers, and this thing is called the transferability property of adversarial examples, and you will understand in a moment why it's called like that. So here is this experiment from this paper by Liu et al., where they took a few models and classified and trained it on ImageNet. And you see that the top 5 accuracy is quite good, it's about 90%. Then they take one of these models, let's say it's ResNet 152, and they attack it using FGSM method. It's just a white box attack, and they get 32%. We've all seen this already. But now they took these adversarial examples generated by ResNet 152 and fed it to all these other models. And these are the numbers that they got. So they managed to reduce the accuracies from around 90% to about 50 or 40%. So are you going to stress that again? Adversarial examples generated by one model manage to destroy the accuracy of other models, which we have no idea what else was there, except that we know the data that they were trained on. And this, yes?
You said that we trained this new model, ResNet 152, on the data that we suppose was used in training of the original models. But does it make sense to train, for example, new model on the outputs? For example, maybe we train new model to predict which output will be in the original model.
I see. I don't know about it. There might be some papers about it. There are a whole lot of black box attacks out there, and this is just one of them with all different assumptions. So I'm showing you this part where you know the data set and you do this attack. Believing there are a lot of papers out there. I can maybe you can look at it together later and look for stuff that you said. But the interesting part, let me just finish with the numbers here. So these are the white box attacks numbers. You see it reduced the accuracy. And these are the black box attacks. So this is just taking adversarial examples generated by one network and feeding to the others. And you see on all parts that it managed to reduce the accuracy. So this property called the transferability of adversarial attacks, adversarial examples, is an interesting property. And you can ask yourself why it happened and try to understand. And again, I don't think there is a full theory of it. I'm pretty sure there is not. But there are some hints. So one possible reason, and I'm gonna borrow a Goodfellow's slide here. So he trained two logistic regression classifiers on the same data, which is just classifying 3 and 7 of MNIST. And after doing so, he checked how the weights of the classifier looked like. And you see that the weights looks quite similar. It means that the classifier learned to note the same features in the inputs. And this might hint that they may be susceptible to similar attacks. So this is one direction. Another very good paper about this is this paper, again from Adri's lab. And they also claim that they have some really interesting experiments showing that the adversarial examples may come from the data itself, which is very cool. This is why hint towards why it works. So let's summarize what we've seen so far about adversarial examples. So remember the bigger picture. We've only talked about perturbation attacks, which is usually what people think of when you say adversarial examples, but still there are a whole lot of adversarial attacks on non-classifiers or different norms, which some of you asked, or just failure cases. This a whole lot of things. So remember the bigger picture. Remember, it's hard to attack. You need to find adversarial example in the box, which is, we've seen FGSM, we've seen PGD, but who knows? I mean, still, if you found one or you haven't found, you ran PGD on your image and you got another image, you fed it to the classifier and still it was correct. Does it mean that there is no adversarial example there? You don't know. You only used one attack. Maybe another attack would find some other adversarial example in this box. And it's much harder to defend, because in order to defend, you need to somehow prove that there are no adversarial examples in all the box. So I'm going to stress, you have to prove it. If you're not going to prove it, you cannot claim that your model is robust. If you cannot prove that there are no adversarial examples in your box, maybe you can prove that it's just very hard to find them. So in this line of work, there are some really neat papers, but they are not practical at any sense because the epsilons they are using are very, very small. But I think this is a very nice direction where the research is going, where you need to prove that your model is robust, provable robustness. If you are not willing to do stuff like that, you can at least evaluate your model very, very well. Make sure it's very hard to find adversarial example in the box. And I'm saying it because there is a lot of papers in recent years that were published only to find a few days later that you can break them and they are not really robust as they claim. It's really, really common. So here's an example how you don't build a fence between the US and Mexico. This is about robustness and adversarial from the security side point of view. So attacking your model and trying to defend against and making it robust. But apparently there are some really cool things happen when you train your model to be robust. So I want to come back to this example I showed in the beginning of this pig, where we tried to, yes, sorry, yes?
Sorry, the question, when you said that you need to train on the same data, the new networks, so when you train on specific network and then try to fool the other networks, they also use the same data, the exact same data?
Yes, so the example that I showed you here, were all models were trained on the same, on ImageNet dataset.
And if you just choose, let's say, images from the same, with the same context, but not the same images, so it's
a good question. I'm pretty sure people have shown it. I don't know the answer. If I have to guess, I would say that even if you're going to use a subset of the dataset, it would still work because you're still learning these features.
No, not a subset, but let's say like the same context, but not the same images.
So that's what I'm saying. Like, you're gonna use just different images of cats or dogs. Yeah. I don't know the answer. It's again, it's very empirical, right? You can just try it and see. I'm pretty sure there are people who have done it, but I don't have. If I have to guess, I would say that yes, it would work. But I didn't try it myself. I don't know. We can look for some papers if you want later. So we're gonna end with this subject of some cool stuff you can do with adversarial training. And if you remember this example I've shown of following the gradient with respect to the loss with the pig, and then we got this image of a fire guard, more or less. So actually, as the story goes, Christian Szegedy, before he published his paper about adversarial examples, he actually thought, well, he didn't think of it at all, that adversarial example. He thought, maybe let's take these classifiers, which are really, really good at classifying. Let's take this image of a cat and start following the gradient with respect to the loss. And because the representations that the classifier learned were so good, so he believed, then the image of the cat would start to appear like another class. So if you just follow the gradient long enough, you would hit another class. Let's say it's a dog, and your image of a cat would turn into a dog. That was originally what he thought would happen. And after trying to do this, that's what he ended up with. So the image of the pig does not even remotely resemble a fire guard, but the classifier thinks it is a fire guard. So this is how kind of adversarial examples were born. This is the fire guard. Or the same goes with this example that I've shown. We try to fool the model to make the pig to look like an airliner, but all we got was this similarly looking pig, which the model is really, really sure that it's an airliner, but nothing changed in the image itself. However, this is by following the gradient of the model. Apparently, when you take a robust model, which is a model that you train adversarially, like we've just discussed now, you're gonna take the model, train it using a PGD, and then do the same experiment that I've just told you. You're gonna take the image, some image, and start following the gradient as far as you can until you hit some other class. You're gonna see what you get. So these are two original images of a primate and a bird. This is what would happen with a standard classifier, right? You're just going to end up with some random noise for human being. And the class changed from primate to dog, but the image did not change at all. And when you take a robust model trained with L infinity, this is what they got in this paper. So this is really neat experimental results of these guys, again from Madhuri's lab. And this is what they got for the bird image. So this is just taking a robust model, following the gradient with respect to the input and very far until you hit some other class. And you turn this image of a bird into an image of the dog, but you also got this human perceptual appearance in this image. And when they train it using L2 norm, they get even better visualization. So this is really cool feature of robust model, which they even published a follow-up paper where they generate random images by only using robust classifier. So here are some examples. Here are also some examples of dogs, birds, primates. And they also show how they can do some other vision tasks using this robust classifier. So super resolution, inpainting, all sorts of stuff. It's really urge you to read. It's a really cool one. And also another guy reading their paper showed that you can actually make style transfer work better for some models when you train them robustly. So this is about it. Time is done. So just to summarize what we've seen today, we saw a few adversarial examples. We discussed what they are. We learned how to attack with FGSM and PGD. We saw how to kind of defend using adversarial training. We got some view of adversarial training, black box attacks, and we saw some surprising visual properties. And that's it. So I will stay here if you have some questions. And thanks all for listening.